right, good afternoon. My name is Karen Winey. I joined the Materials Science and Engineering Department as an assistant professor in 1992. That was the year the LRSM directorship transitioned from Ward Plummer to Mike Klein. Sorry, for a moment, I can't remember Mike's name. Okay, so I took a somewhat different tactic in putting the talk together. I was asked to talk about carbon-based materials. And for me to stand at the LRSM and talk about carbon-based materials, I cannot start with my own work. I have to start with the work that happened long before I got here, and that's really the work based on polyacetylene. So we're going to start there, and then we're going to rapidly get up to current times. So we've heard a lot about this combination of collaborators from chemistry and physics working on polyacetylene, conducting polymers, but I went back and I found the paper. It's actually a pretty easy read. It's about 2 pages. It has 2 chemical structures drawn in the paper. Trans polyacetylene, like shown here, but it's also drawn in the cis format. Really, any sophomore level chemistry major could draw those structures. And this is the figure in the paper. It's not even figure 1. It is just called figure. And Heeger and McDermott's first paper was this is from '77. They first started publishing together in '75. So just 2 years later, after working on sulfur nitrides for a little bit and linear chains of mercury to find a new conductive materials, they found the winner, right? Polyacetylene in a film, and they were exposing it to iodine vapor. And as they did that, you could see this dramatic increase in the electrical properties, right? So 7 orders of magnitude. And this paper contains the key sentence: this material has the largest room temperature conductivity observed in any covalent organic polymer. Right? Remarkable finding. So this is the short paper. This is the 1-figure paper. The paper describes other results as well with other dopants, but they only showed the data for the iodine. So this is the long paper. This one had 3 figures. I'm not telling my students that this is what papers are like, right? So this is in PRL then, and again, it's many of the same people, but in this case, they've doped polyacetylene, and now the order of magnitude increase in the electrical conductivity is on the order of 7 orders of magnitude, right? So it's hard for us to appreciate how novel the combination of chemistry and physics together was at that time in the late 70s. Again, critical that the LRSM was here to bring them together. And that resulted, of course, in the Nobel Prize, and the actual wording is for the discovery and development of conductive polymers. So when I was a graduate student and I came here to interview, I already knew that Penn had polymer people, right? When I told my degrees from the University of Massachusetts and the Polymer Science Department there, they all knew that there was polymer work going on at Penn. And so it was a great honor to come to Penn because of this earlier work. All right, there are other forms of carbon besides polyacetylene, and probably the next one that features prominently within the LRSM history is C60. So Jack Fisher's been mentioned a number of times today. This is one of his key papers. It includes Paul Winey. There's Jack. Andrew McGee. Wow, we keep talking about Drew, right? And Bill Romanow, right? It was mentioned earlier that Jack had a habit of publishing with staff scientists here at Penn. And then Amos from chemistry. Also highlights an interaction with national labs at B&L. So this nugget of work was critical in determining that C60 actually formed crystals. And at room temperature, each C60 molecule spins, so it's isotropic, and it packs the way billiard balls would, or ping pong balls, right, with all spherical symmetry. So if atoms have good spherical symmetry, they pack in an FCC crystal, and that's what happens at room temperature. But when they went to cryo temperatures, it switched to simple cubic. And if all you can get is kind of the scattering in this range, yeah, you're gonna think you still have FCC. It's this range which changes a lot, from FCC to the simple cubic, right? And so that's the orientation ordering transition. So for things like methane, it happens at a much, much colder temperature. But because these are larger molecules, this orientational ordering transition happens actually in the high 200s. I think it's like 249 or so for that transition. After C60, you have carbon nanotubes. This reflects Jack's very long and fruitful relationship with Rick Smalley. This is the student, Roland Lee, who did most of his work here in the LRSM. And so this is a key paper within the carbon nanotube community because it did a couple things. It actually identified them as being crystalline ropes. So when the single-wall carbon nanotubes are uniform enough in size, they'll pack into this hexagonal lattice or triangular lattice. And this lattice parameter is why this paper is quoted so often, because it actually allowed this crystal structure of the carbon nanotubes is allowed to give you, provides a method for giving you a diameter of the carbon nanotube. Right? Very highly cited. And it's also is coupled with this electrical measurement for these, this rope of metallic nanotubes. Now, I believe there's only one micrograph, possibly ever, where you can see the rope end on like this. But it might not look familiar. It looks more familiar when it's rotated and cropped, right? But if you can, this is exactly the same figure, rotated and cropped, and this, in this cropped form, is one of the figures in Bauman's Science Review about carbon nanotubes, which has been wildly cited, right? That was done here at the LRSM, Roland Lee. Okay, so if you've got C60 and you've got carbon nanotubes, the next step would be to put them together. Oh, sorry. One other thing. So Jack did not win a Nobel Prize, but we did have a really good party for him. So in 2009, we got to celebrate Jack with the Jack Fest. All right. If you take C60 and carbon nanotubes and put them together, you can actually fill up the carbon nanotubes with the C60 molecules. Really a remarkable bit of materials processing. And the fact that the carbon nanotubes want to tuck into a single-wall carbon nanotube is really cool statistical mechanics. And Lou Giafalco has made incredible contributions in that area. These materials have also been studied with scanning tunneling microscopy to look at how the electronic structure changes when it's filled or when it's not filled, right? An interesting collaboration now involving some of the chemistry along with Dave Leslie from the Material Science Department. All right. Only 2 slides on my own work. So Jack is very enthusiastic, and he can sell ice to the Eskimos. So it was actually a much easier job to convince me to start working in carbon nanotubes. And so Arjun's group has done important work with trying to get nanotubes dispersed in liquids. It was nice to see Mohammed Islam. I don't see him in here. He might be in the other room. Really key work on selecting which surfactants are necessary or do the best job of getting the single-wall carbon nanotubes exfoliated in liquids. We worked on getting nanotubes suspended into polymers. This is our first paper in 2000. We got high amounts of orientation. And then when we started measuring the electrical properties of these fibers, we found some unusual things. So we decided it was time to do simulations, which is not my strength. Brian Dodona is a former postdoc. We found him when he was no longer postdocing here at Penn, but was postdocing out at Minnesota. And he helped us develop, well, it was his program. We encouraged him to develop it further, actually make electrical measurements. So now we can simulate the electrical conductivity as a function of orientation, and we control the orientation with how we process the fibers and measure the extent of orientation with X-ray scattering. Right? This paper, this set of simulations is expanded considerably. We now can take random distributions of nanotube sizes, and take random distributions of orientations and compute what the electrical conductivity is. We're now expanding this into looking at 2-dimensional materials for metal, nanowire, 2-dimensional transparent conductors. So that's not carbon anymore. We're going into metals. And then the other one is, I hope Ward Plummer can hear me, wherever Ward is. The accelerator is alive and well. It's behind the reading room. It's alive and well. Ward and Russ were able to bring the ion beam accelerator here. We're collaborating on the project initially as part of the LRSM, but then, like many good projects from the LRSM, they go on and get their own independent funding. We now have separate NSF funding for the project. This is from the ion beam tool, the instrument where we can look at the depth profile, the depth concentration of deuterium, so we can see how polystyrene, initially in a thin film on the top of the composite, can diffuse in. The diffusion problem in polymer nanocomposites is fascinating because polymers have a certain size. Nanoparticles are smaller than that, but not nearly as small as solvent molecules. So there's this interesting coupling in the size, the polymer chain and the particle size, and we really have seen remarkably unexpected and to date unexplained differences in how the polymer, what the polymer dynamics are. So in one example, we see the diffusion coefficient decreases as you add carbon nanotubes, and then it recovers. And it was wonderful to have Ken Schweitzer here earlier this year. I think we really piqued his interest, and he piqued ours in trying to look at the fundamental reasons why polymers are moving differently in the presence of nanoparticles. And then the last one, if we're staying on the topic of carbon, we must mention graphene. Charlie and I exchanged emails last night, and he picked this one as his currently favorite paper. So this is in collaboration with Andy Rapp, again, chemistry and physics. And the difference being really a synthetic route that, now who do you think did the synthesis here, right? The guy in chemistry or the guy in physics? The guy in physics. The guy in physics, that would be Charlie, developed a synthetic way, CVD method, for growing graphene so that you get this sort of edge instead of this sort of edge, a zigzag edge instead of an armchair edge. Right? And that significantly changes the electrical properties of these little sheets of graphene. And the mechanism for that growth is better understood after the DFT calculations. That's the Andy Rapp contribution, right, on how the carbon can move on top of a polished copper surface as it grows onto the graphene. So that is my whirlwind tour of carbon within the LRSM. All right.